Hyperbolas. So this lesson we'll be looking at the rule for a hyperbola and alternative ways to describe it. So we define them analogously to ellipses, but we use the difference instead of the sum. So a hyperbola is the locus of a point that moves so that the difference between its distances from two fixed points remains constant. These two fixed points are the foci as they were with the ellipse, and so the difference between these distances here remains the same. The standard Cartesian form of a hyperbola centered at the origin is this. So as you can see, the same as an ellipse, but we've just got subtract. We're finding the difference instead of the sum. If we translate the hyperbola, then we get this. And this is a hyperbola centered at the point HK. And I'll speak about what the center of the hyperbola is in a moment. If we interchange the x and the y, so if it's something with y's minus something with x's, then that results in a 90-degree rotation. So these things which are currently kind of vertically would become kind of horizontally. To find the equations of the asymptotes of a hyperbola, which would run down here and here, we need to rearrange the equation. So I start by adding y squared over b squared to both sides and subtracting 1. Then I multiply by b squared and factorise. Now as x tends to infinity, positive and negative infinity, then this fraction here will tend towards 0. So this whole bracket here will tend towards 1, and our y squared will tend towards b squared times x squared over a squared. So if I square root both sides there, then y will tend towards b x over a, as x tends to positive and negative infinity. And this is positive and negative bx over a. And so these give me my two asymptotes, which we can now see here. This is the centre. Where the asymptotes cross is the centre of the hyperbola. So it's not actually a point on the lines itself, it's where the asymptotes cross. If we translate our hyperbola, then we get this situation where this general form of the hyperbola gives asymptotes like this. So rather than having to actually rearrange the whole equation each time, we can just note that the gradients of the asymptotes are b over a, positive or negative b over a. So let's have a look at a few examples. Here I can rewrite this as x squared over 3 squared minus y squared over 2 squared. So using this idea, I can see that there's asymptotes at positive or negative 2 over 3x. I haven't had any translation going on, so I'll get to that part in a moment. I need to find my x-intercepts. They occur when y equals 0. When y equals 0, x squared over 9 equals 1. So x squared equals 9 and x is positive and negative 3. And there have been no translations, so the centre remains at 0, 0. And this is what my graph looks like. When sketching hyperbolas, draw in your asymptotes first and make sure your intercepts are symmetric. If your centre's at 0, 0, make sure this distance is the same as this distance, and then sketch the lines in. This one here, you can see the y and the x have swapped around. So I can rewrite it with the 3 squared and the 2 squared. This gives me asymptotes at y equals positive and negative 3 over 2x. So the y has the b in the denominator and the x has the a in the denominator. This will have y-axis intercepts. So if you're wondering where are the x-axis intercepts? If this was equal to 0, then this would be negative. It doesn't make any sense for this to be negative because it's a squared over a squared, so that's impossible. So we know there must only be y-axis intercepts at 3, 0 and negative 3, 0. That was calculated the same way as we did the x-axis intercepts over here. Centre is at 0, 0 because we haven't had any translations, and so this hyperbola would look like this. As you can see, it's a 90-degree rotation of the first one. Pause the video now and have a go at question 1. You might need to do a little bit of rearranging for D. And this is what you should have got. Okay, so let's look at some slightly more complicated ones. First, let's just consider what happens if we have x squared minus y squared equals 1. That would give us asymptotes at y equals positive and negative x, because we're not dividing by anything here. My centre would be at 0, 0 for this simplified version. Here, and my x-axis intercepts are 1 and negative 1. This is called a rectangular hyperbola as the asymptotes are perpendicular. If we apply the translation, then our new centre is at 1, negative 2. And our new asymptotes, I just take this and substitute in y plus 2, x minus 1. Because I know that the asymptotes intersect at the centre. So y plus 2, or y subtract negative 2, equals positive and negative 1 is my gradient of them, minus 1 times x minus 1. And so I've just rearranged that to get the equations in the form y equals mx plus c. And then when x equals 0, y equals negative 2, and y equals 0, I can solve for x to find my intercepts. And so this is what it looks like. In this example, I've got translations and the divisions going on for the dilations. So let's have a think about this one first without the translation. That gives me this hyperbola here. This is my b because it's in the denominator of the y. This is my a, so it's the square root of this over the square root of this for my equations of my asymptotes. Then I apply the translation. My centre is then going to be at negative 2, 1. And then for the equations of the asymptotes, I substitute in the point negative 2, 1. I know that the original gradients were 2 over 3 and negative 2 over 3. So my new asymptotes are here and here. And then I simplify to write them in their normal form. Pause the video now while you have a go at question 2. And here are your answers. So we might also have to answer questions algebraically. So here we're given that the distance between the points remains constant, not between the points, between P and A and B. So as we've done before, I let x, y be the coordinates of P, then set up an equation using the distance formula. As I did before, I want to add this one. It makes more sense just to add this one to both sides. Square both sides and expand the brackets. Simplify. Then I want to subtract this 9 because then I'm going to square this and that will get rid of my square root. So we've got this. And then I divide to make it in its standard form. So this gives us the right branch of a hyperbola with the centre at 0, 0 and the x-intercept at 3/2. Pause the video now while you have a go at questions 3 and 4. Here's your answers. Ideally, this we'd have divided by 20 here. So an alternative way of defining a hyperbola is it's the locus of the points pxy satisfying fp equals e times rp, where f is a fixed point, e is greater than 1, and rp is the perpendicular distance from P to a fixed line. And from the symmetry, we get the other branch of the hyperbola. So we can use this definition to find equations of hyperbola 2. I'll give you a moment to read this one. So here's a sketch so we can picture what we're calculating. We've got our point P, so I know that the distance from P to F here is equal to 2 times my distance from P to M, the line. So I can square both sides. Make sure you remember to square the 2. Expand the brackets. Rearrange. I need to complete the square here. Factorise the 3 out first for the x's. And then finally I can divide by 12 to get it in its standard form equal to 1. So we've got the centre at -3, 0. And these are the equations of my asymptotes. Pause the video now while you have a go at questions 5 and 6. And these are the answers.